Alright, so this is Unit 3 extra practice. I'm just going to go over them with you and try to explain how she explained them to me. I'm going to do 1, 2, and then I'm going to come down and do 5 for you. And if I think those are the ones that you were asking about. And if you need more explanation, if they didn't make sense, whatever, I can try to go over them again for you. Okay, so starting for number 1, we're going to name these molecules. So, starting with 1, 1, we're going to first find how many carbons are in the main carbon chain. And we're going to start at this triple bond right here. So there's 1 carbon right here, 1 at the end of the double or triple bond, carbon right here, and everywhere that I located is a carbon. And then we have this right here, which is actually not part of the parent chain. It's like another thing added onto the carbon chain, which I'll go over in a second. So first I'm gonna label these carbons, and we see that there is a triple bond right here, which is a priority group. So this needs to have the lowest number. So we're gonna start labeling right here, and it's gonna be 1, 2, 3, and so on. So I'm just gonna do that real quick. And we see that there's 6 carbons, and we know that 6 carbons is hex, and we have to figure out the ending of that, which is based on the bonds. And we see that there's single bonds all over here, except for once we get to the first and second carbon, there's a triple bond. And a triple bond is alkene, I think is how you pronounce it. Where this part actually is going to add on to the hex. And we know that's on the first carbon. Then we're going to look at this group right here. We see that it has 2 carbons, which is then attached to an oxygen, which is then attached to the primary carbon chain. We know that when there's 2 carbons, it's an ethyl group. And this ethyl group right here is actually attached to an oxygen, so that's ethoxy. This whole thing right here is actually ethoxy. And we know that's on carbon 4. So we're going to go 4 ethoxy. Then these are going to be at the end of the name. So we're going to start this with 4 ethoxy. Then we're going to add this hex. And then we're going to add this YNE. And I'm going to add the 1 because if it wasn't on the first carbon, you'd have to add it. But in this example, technically, you could leave it as this. But just for consistency, I'm actually going to label it 1 YNE. Because if this double bond wasn't on the first carbon, you'd have to label it and identify which carbon it is on. Just like how we do 4 ethoxy, how we know that the ethoxy is on the 4th carbon of that carbon chain. And that's the name for this first problem. Going down to the second one, I'm going to do the exact same thing. I'm going to label and highlight the carbons. Same thing right here. This is not part of that carbon chain because this oxygen right here actually breaks it up. So same thing like it was up here, that's going to be an ethoxy group. Now to figure out which side of this carbon chain we're going to start labeling at, we're going to look at the priority groups, which this double bond is actually the priority group. And this priority group has to have the lowest number. So we're going to start on this side and we're going to label it like that and so forth. So we know this is 6, and just like this problem up here, 6 is hex. And then to find out the ending if it's hexene, hexane, hex whatever, we're going to look at the bonds. We see that everything's a single bond except for between carbon 2 and 3, which is a double bond. And we know that double bond is actually ENE. And that's on the second carbon. So that's why we need to identify that the 2 goes before the ENE. But same thing like it is up here. We're actually going to add this ENE right after the hex once we get the final name. Then, like I said, the only thing attached to that parent carbon chain is this F-oxy right here. We know it's an F-oxy because it has 2 carbons, which is an ethyl group, and that ethyl group is then attached to an oxygen, which that's then attached to the carbon chain. And that is on carbon 5. Now, we could name it like this, but it wouldn't be completely correct because now that we know how to name it with E and Z, we're going to do that. And we pay attention to E and Z only if there's a double bond, which in this case, this molecule has a double bond. So we're going to look at this carbon right here and this carbon right here. And like I was telling you when we were in the study room, I'm going to start directly off with a dotted line right down that double bond. And we know that each carbon, because they're neutral, need to have 4 bonds. And we know this carbon right here already has 1, 2, 3 bonds. So it needs another bond bonded to hydrogen. And if we're looking at this dotted line right here, we see that they already have an attachment above the dotted line. Therefore, we need that hydrogen bonded below the dotted line. So I'm just going to bond that real quick. And then I'm going to look over and see which is a priority group between this hydrogen or this carbon right here. Because we know that this carbon right here is bonded to a C that has 2 H's on it. And another C, whatever. And like the rest of the chain. So now to identify which is the priority group on this carbon, we're going to look at the H in the C. And we know that C has a greater atomic size than H, which therefore means that this is a priority group on this carbon right here, which is above the dotted line. Now we're going to go over to this carbon, and we know that it's not charged, so this carbon needs 4 bonds because carbon is a 4-bonder. And we know that this carbon is already bonded to 1, 2, 3. It already has 3 bonds. So we need to add another bond to make it stable. And the other bond's going to be the hydrogen, just like we did down here. Now, to find if it's either above or below the dotted line that we need to add this hydrogen, we're going to look at what's already bonded to this carbon chain, this double bond. So we see this dotted line that I went through, and we see that we already have a bond below the dotted line. Therefore, we need to add a hydrogen group above the dotted line. And that's how we know if it's above or below the dotted line. Now we're going to look at what this carbon right here is bonded to find out which the priority group is. We know that it's bonded to a C, and then down here is a CH3 group or a methyl group. And we know between H and C, we know that C has a greater atomic size, which therefore means that this is a priority group on that carbon right here. Now looking at the priority groups, we're going to look what side they are on this dotted line. And we see that one's below and one's above, which means they are on opposite sides, which means they are enemies, and that's why they are E. And this E is always going to come first in the name. So that's always going to be first, so I'm just going to add that. And now we know that this is going to be at the very end of the name. And the only thing left we have to add that is at the beginning of the name, other than the E, is this 5-F-oxy. So I'm going to add this right after the E. And now I'm going to add that hex right after that. And I'm going to then add after the hex the 2 and then the ENE. And that's the final name of that molecule. Now, if we go down to question 2, it's asking us to draw the molecules that is set up here, and then we're going to have to rename it because these are all not named correctly. And we're not going to worry about D because that's irrelevant. So, looking at this first one, identify what we know. We know that we have 2 fluorines, 1 chloro, which is chlorine. We have a hex, which that is a 6 carbon chain. ENE is a double bond. And then amine is another priority group, NH2. So we're going to start with drawing our parent chain with that double bond. And now I'm going to number them. We know that there is a double bond on the 5th carbon, which is right here. So from 5 to 6, there's a double bond right there. And then on the 6th carbon, there's an NH2 group. So I'm just going to add that real quick. And then we also know that on the 4th carbon, there's a chlorine. Oh, I did that wrong. Okay. On the 4th carbon, there's a chlorine. And then on the 3rd carbon, which is right here, there's difluorine, which means that there's 2 fluorines. Now, to name this correctly, we need to identify the priority groups, which is the double bond and the amine group, which is down here. These priority groups need to have the lowest number. So I'm going to renumber them having this as 1, or having this as the 1st carbon, 2nd, and so on. And this is going to stay, the parent chain is still going to be 6, so it's still going to be hex. It's still going to end with the EN because it still has a double bond. But instead of it being 5 EN, it's going to be 1 EN. Same with this amine group. That's also on the 1st carbon. So that's also going to be 1 amine. Then we're going to look at the chlorine and the fluorines. The chlorine's on the 3rd carbon, so it's going to be 3 chloro, maybe. And this fluorine, there's 2 on the 4th carbon after renaming it correctly. So it's going to be 4 difluoro. Once again, we could name it like this, but we know how to do E and Z, so we're going to do that. And E and Z only happens at a double bond, which is right here. So I'm just going to label these carbons. Next, I'm going to draw a dotted line right through that double bond. These carbons are not charged, so they need to have 4 total bonds because carbon is a 4-bonder. And we know that both carbons already have 3 bonds. That carbon has 3 bonds, and this carbon also has 3 bonds. So we need to add a bond to each of these carbons, and that needs to be bonded to a hydrogen. Now, looking where this, we're going to pay attention to this carbon first. This carbon is already bonded above the dotted line, so the hydrogen needs to be bonded below the dotted line. And now looking at the H or the N, which is bonded to this carbon, to determine which is a priority group, we know that nitrogen has a higher atomic size than hydrogen, which makes this a priority group on that carbon right here. Now looking at this carbon, looking at that dotted line, and what's already bonded to that carbon is right here, which is below the dotted line. So that hydrogen needs to be bonded above the dotted line. So I'm going to draw that in real quick. Now, to determine which is the priority group, this carbon right here is bonded to a hydrogen and another carbon, which is then bonded to a Cl. So we have to determine if C or H has a higher atomic size. And we know that C has a higher atomic size, which therefore means that this is a priority group. Now to determine if it's E or Z, we need to look at this dotted line. And we see that this priority group is above the dotted line, while this is below the dotted line. And because they're opposite sides of that dotted line, they are enemies, which means that is E. E for enemies. And the E or Z always comes first in naming, so we're going to just put the E right there. We know that all these priority groups are going to go at the very end of the name. So now we just need to pay attention to this to find out which goes first in the name after the E. And that goes by alphabetical order. And we know that chlorine comes first before fluorine. So it's going to be 3-chloro, 4,4-difluoro. Hex then comes next. And then to determine which one's up the priority group after this one, after the hex, it's going to come ENE and then the amine. Now, because ENE ends with a vowel and amine starts with a vowel, we're just going to take that end E off, and it's just going to stay EN, and then we're going to add that one amine. If we wanted to, we don't technically have to add these ones like I was talking about earlier, because if we just left it like hex, ene, amine, we would assume that the double bond in the amine group are both going to be on the first carbon, which this molecule shows that they both go on the first carbon. But just for the sake of not forgetting it when it matters, like up here, how that 2 does matter and does need to be in the name, I'm just going to add the 1. And that's why on the study guide, you can see it better on the next problem we're going to do. She has 2 names. They're the exact same name, the exact same molecule, just she left out the 1. All right, now let's add this next one. I'm going to do the exact same thing, go over what we know. We see that there's a bromo and a bromo. We know that there is a hydroxy, which hydroxy is an alcohol group, so that's OH. We know there's a cyclohexane, but in this case it's double bond at 4, so we know that that's hex is 4, so that means it's going to be a cyclohex. And then ENE indicates a double bond at the carbon site 4. So I'm going to start with doing the cyclohex 4-ene. I'm going to number them. We know that at the 4th carbon there's a double bond, so I'm just going to add that in real quick. So the carbon 4 going to 5 is going to have a double bond. We know that there is an alcohol group at the 5th carbon, which is right here, so I'm going to add an alcohol group. And we know there's a bromine at both carbon site 1 and 2. So I'm just going to add that real quick. Now, looking at which is a priority group, the alcohol and the double bond are both priority groups, which start at this carbon right here. So when we're naming it correctly, we're going to have carbon 1 go this way, and then it's going to go around like that. So I'm just going to rename it real quick. 1, 2, 3, 4, 5, 6. And now it's going to stay the cyclohexane. So cyclohex is the exact same. Now we know there's a priority group of alcohol at carbon 1. So that's actually going to be OL, not hydroxy, because it's still a priority group. So 1-ol. There's also a double bond going from carbon 1 to carbon 2. So that's going to be 1-ene. There's a bromine at carbon 5 and 4. So it's going to be 4,5-dibromo. And we could definitely look to see if it is an E or a Z, but this carbon and this carbon actually have, they're not both chiral atoms, because this carbon right here is actually bonded to a hydrogen, and then this is the exact same as that. So E or Z does not matter in this molecule. So we know that this all is going to be at the end because this is all priority of the name. So we know that the 4,5 dibromine has to start the name. Then we're going to add the cyclohex. And then out of these two priority groups, the ENE is going to start after the cyclohex. However, ENE ends with a vowel and OL starts with a vowel, so we're not even going to add that last E. So it's going to be 1 EN, 1 OL. And that's a name. Once again, we could just keep it, we don't even have to add the ones, we could leave it like this, and we could still be determining that the double bond in the alcohol group are both on the first carbon. You could, like, in this key, she indicates that you could do it both ways, however way you want to do it. Same with like we did up here. Okay. Last problem for question 2. We're going to do what we know. We know that E means enemies, but that's going to be the last thing we do. Pent right here, we know that is actually going to be 5. ENE is a double bond, so we know there's a double bond at carbon 3. And propyl is going to be just like this, which has 1, 2, 3 carbons, and then this is going to be bonded to the parent chain. So I'm going to start with drawing the 5, the parent chain. I'm going to add a double bond at carbon 3 after I label and number this. Double bond at site 3 to 4. Then there's a propyl at site 2, which is right here. Now we're going to determine if we did this correctly by making it E. So we see this double bond right here. These are the 2 carbon sites that we're going to be worried about. I'm going to highlight those real quick. First thing first, I'm going to do a dash through that double bond. We know that these carbons right here are not charged, so they need to have 4 bonds in total because carbon is a 4-bonder. But so far, this carbon only has 3, and same with this carbon, only has 3. So we need to add a bond to hydrogen to make this a neutral carbon. Looking at this carbon right here, we see that we already have something bonded to below that dotted line. So we need to add that hydrogen above the dotted line. And this right here is actually a CH3 group. And to determine priority of that carbon, we're going to look at hydrogen or carbon to see which has a higher priority because of the atomic size. And we know that carbon has a higher atomic size than oxygen. Therefore, this is a priority group. Now looking at this carbon right here, we see that there's something bonded above that dotted line, so that hydrogen needs to be below that dotted line. Same thing, this is a carbon right here. So now we're looking at this carbon is bonded to a hydrogen or a carbon, and we know that carbon has a higher atomic size than hydrogen, which means that this is a priority group over here. Now to determine if we did this correctly with E or Z, we're going to look at that bond or that dashed bond, and we see that 1 priority group is below and 1 is above, which means they are enemies because they are on opposite sides, which means that that was E, which means we did that correctly. Now, to name it correctly, we know that this is the only priority group. This double bond is the only priority group. So we need to make sure that this has the lowest numbers. So we have to label it that side, going like that, which is the opposite of what we have labeled now. So I'm going to relabel it correctly. However, we can make this carbon chain even longer by adding the carbon chain up on this. So instead of it ending right here, we can make it even longer and go up there, which is what I'm going to do. Because we always want the longest carbon chain that we can get. So we have this as the new parent chain. And that's 7. And we know that 7 is hep. We know there's a double bond at carbon site 2. So that means it's 2-ene. We know that it's still E because we didn't change anything. So this is still an E. And then we have this methyl group right here bonded to carbon 4. So it's going to be 4-methyl. E always comes first in the name. We know that the hep and the ene are going to come last. So the only thing to add right after E is that methyl. And now we're going to add hep from there, and then 2-ene right after hep. All right, and that finished naming this molecule right here. And we don't have to worry about D because we didn't learn how to name this structure correctly. So we're just going to skip D. And we're going to go all the way down to 5 because I believe that's what you were asking, unless you were asking for 3. But if you need to know more on this, just let me know. So for this, we are determining if they are constitutional isomers, enantiomers, diasteromers, meso compounds, or if they do not have a isomeric relationship. So we're going to look at A real quick first. And we're going to determine if it's R or S. A quick trick for me that helps you remember is if we're doing clockwise, looking at a clock, it goes to the right. So clockwise is right, and right starts with an R. So if it's going this way, it's R. Okay, so for this, now we have to determine which of these are priority group. We know that this carbon is bonded to C, H, and Br. We know that bromine is the highest atomic size, therefore it's the highest priority. And we know that hydrogen is lowest between these two carbons, so that's going to be the last. Now to determine which is second priority and which is third priority, we can't just look at the carbon because they're both carbons. They both also have 2 hydrogens. So now what we have to look at is what comes next after that. This carbon right here is actually a methyl group, so it's actually like this. And then this right here looks like this. And looking at these two, we already determined that they both have C's connected to that chiral carbon. They both have an H and another H. So now it comes down to either this carbon or this hydrogen, which carbon has a bigger atomic size, therefore this is the second priority group. And then the methyl is the third. And then we can see that it's going counterclockwise, which is S. We also see that hydrogen is on that dashed bond, which is good because it's exactly what we want it to do. So we don't have to change anything about this S or R or switch it or do a Newton projection, anything like that. We can leave that as S. Now for this molecule right here, the priority groups are going to stay the same. So bromine's still 1. The ethyl group's 2, methyl is 3, and hydrogen is 4. However, this hydrogen is not on the bond or the dash bond, and it's not next to the dash bond either. So we can't just simply switch and reverse S to R, R to S, or whatever. We have to do a Newton projection. And we're going to do this Newton projection looking directly down at the H, so the H will be actually like below or behind the Newton projection, I mean. So to do that Newton projection, we know that Br is above, ethyl is to the right, and the methyl is to the left. So I'm just going to put those in real quick. And the priority groups stay the same, so bromine's first priority, ethyl is second, and methyl is the third. And then if we go in the direction that the priority groups are going, from most priority to least priority, it's clockwise, which is R. So now we know that this molecule is R and this is S, which means they are opposite, which means that they are mirror images, which means that they are enantiomers. I think I spelled it wrong. I did. Okay. Now looking at this molecule right here, first we are going to look at this and determine if this is a chiral atom or not. If it is a chiral atom, then we can determine if it is an enantiomer, diasteromers, or meso compound. If it's not a diasteromer, then we need to look at the formula and the connectivity. So this carbon right here is bonded to a CH3 group, a hydrogen group, and then these are the exact same. So this is not a chiral atom because it's bonded to the exact same groups. Same with this molecule right here. It's bonded to a methyl, a hydrogen, and then these are the exact same groups. So this carbon right here is not a chiral carbon. So it's not an enantiomer, not a diasteromer, and it's not a meso compound. Now we need to look at the formula. They have the exact same chemical makeup, exact same formula, exact same connectivity. Therefore, this is the same molecule because it has the exact same connectivity. So it's a no isomeric relationship. Okay. Now, going to question C. This is a chair. So chair. So I'm just going to make it into a cyclohexane because it's easier for me to identify in that manner. Oh my gosh, I can't draw. Okay. Okay. Now I'm going to label these 1, 2, 3, 4, 5, 6. Hold on. Yeah. No, I'm going to do it the other way. Okay, what is happening? All right, and now we remember that a dashed bond is pointing down and a wedge bond is pointing up. So looking at this, both of these bonds are pointing up, so both of these alcohol groups are going to be on a wedge bond. And we know that it is on carbon 1 and carbon 2. So on carbon 1, we have a dashed alcohol, and as well as on carbon 2. Okay. Now looking at this right here, on the first carbon we have a bond pointing down, which means that it's a dashed bond, and on the second carbon it's pointing up, which means it's a wedge bond. So that's what this molecule is going to look like. And we know that diasteromers is when you change one bond. So you change one bond from a wedge to a dash or a dash to a wedge. Which is exactly what we did, because this stays the same. They're both wedges, but these are different, because this is a wedge and this is a dash. So that makes these diasteromers. Now, looking at these, first we have to determine if we can even identify if they're enantiomers, diasteromers, or meso compounds. We need to see if we have a chiral atom. So we're going to start right here. We know that this carbon is connected to a carbon, a hydrogen, and another hydrogen. Because it's connected to the exact same thing right here, that's not a chiral atom. So now we have to look at the connectivity in the chemical formula. We see that they have the same formula, but they have different connectivity. And we can tell this because on this molecule, the chlorine is by itself, whereas the chlorine is attached to a CH2 group. This makes these a constitutional isomer because they have the same formula, but different connectivity, and they are not enantiomers, diasteromers, or meso compounds. All right, and that solves those. If you have any more questions, let me know. I can try to help you. If any of this is confusing for you, again, just let me know. I'll try to go over it, slow it down, put in different words, whatever will be helpful for you.